All right, good morning. We're running just a couple minutes late here. All right, so today we're going to continue with water softening. I have not yet posted your homework, so I'll do that later today. Just looking at our schedule, we have today's lecture, Tuesday's lecture. A week from today, I have to cancel that class for another commitment. And then I think that means the 31st would be an exam review day, and I think our next exam is on November 2nd. So that's kind of a quick update about where we are. So you'll have over a week for the homework if I post it today. And you'll have seen pretty much all the material you're going to need for that. Okay. So with that, last time we left off talking about this concept of equivalent weights, useful for both alkalinity and hardness, and kind of even helps us see the connection between the two in some sense. So we talked about each of these steps to get the equivalent weight, and then we took a look at just kind of a table. We could formulate a table with all of these pieces. Just a matter of looking up the atomic weights or calculating the molecular weights, taking a look at their charge, and that's the charge, that how many protons it would take to account for the same number of either negative charges or to replace the positive charges, right? So we could go back and look. It's that ionic charge or number of hydrogen atoms required to replace, or you could maybe say replace the cation or satisfy the anion. All right, so with that, I think we left off here. This is an example that we can work. So we have a sample of groundwater, has 100 milligrams per liter of calcium and 10 milligrams per liter of magnesium. Then we're asked to express its hardness in units of milliequivalents and milligrams per liter, both per liter, as CaCO3. Okay, so I want to go ahead and just start us there, get our brains in motion. So what I will do is I'll flip back for a moment briefly to just simply write down what is our equation here for the equivalent weight. That is going to be this in milliequivalents. It'll be the concentration of, well, first of all, it's the molecular weight divided by N, right? And then we have the conversions that we can do from there. So we'll just write that. I'm going to say molecular weight divided by N. Okay, so take a few minutes and work on that. so you've had a few minutes to work on this, and what we'll see here, I've started the problem with starting with calcium. If we take a look back, so we have this equivalent weight value here, and really what we need is to calculate the effective hardness in both of these forms. We were asked for it in milliequivalents and milligrams CaCO3, and so we can just take each of the components and then add them together once we've calculated for their respective contributions. So at the end of the day, it really is coming down to just handling the units appropriately. And the slide we had here gives us kind of a quick and easy roadmap, right? So we have the formula for equivalent weight. That was the molecular weight divided by N. So maybe I should have written that as a formula itself. But from there, we can recognize that to get milliequivalents, what we need to do is divide the concentration in milligrams per liter by this equivalent weight. Okay, so then fast forward a little bit, I took calcium, we had 100 milligrams per liter. I said, well, if we want to find this milliequivalents per liter, that's going to be the 100 milligrams per liter divided by that equivalent weight, which is given here, or we could look it up, or calculate it. That's 40 divided by 2, essentially. So that gives us 5 milliequivalents per liter, not 50, as an answer there. From there, we can see that we can get a conversion to milligrams per liter as CaCO3 if we know the milliequivalents, because then we can recognize that CaCO3, and this was from what we solved last time, if we were to write it here, CaCO3 here would have an atomic weight, or a molecular weight rather, of 100, a charge equivalence of 2, that would give us a 50 milligrams per milliequivalent. So that's calcium carbonate. I'll write it a little clearer. And that's one that might be worth just committing to memory. CaCO3 is 100. And then with a charge of 2, that becomes that equivalent weight of 50. So this is the simple way to do that. We'll see this in our slide here. If we want milligrams per liter of X as CaCO3, we can take the concentration divided by the equivalent weight, which that's our formula for equivalent weight, right? Or excuse me, that's the formula for our milliequivalents per liter. Multiplying that by the conversion to go from, it's 50 milligrams of CaCO3 per milliequivalent. So doing that gives us, oops, I just went all the way to the end. Gives us this 5 times 50 milligrams of CaCO3 per milliequivalent. That should give us a conversion that says 250 milligrams per liter as CaCO3. Okay, so we can do the same thing for magnesium here. We've got 10 milligrams per liter, so if we take, if we want to find the milliequivalents per liter, we'll take, we'll say that's going to be the 10 milligrams per liter, and divide that by the equivalent weight for magnesium, which would be 12.2. So I haven't done this yet, but that's going to be a little under 1. Should be 0.82. Okay. So from there, that's milliequivalents per liter. And now we can take that one to get our milligrams as CaCO3 and say milliequivalents per liter from this magnesium times 50. If we want to be explicit, by the way, we could say 50 milligrams CaCO3 per milliequivalent, right? And that's how we're transferring our units. Milliequivalents is a charge equivalent. So that's going to be, we don't have to specify that's, that would not be directly related to the magnesium here. Okay, so I'm going to go back to my calculator, show you what I'm doing. So this is the 12 divided by 10 divided by 12.2, multiply that by 50, and we'll get essentially 41. Milligrams per liter, we'll notice that the per liter stays, the milliequivalents will cancel, the milligrams as CaCO3 will remain. Okay, so then from here we've got basically all the data we need. We just have to add up the two components. So on the milliequivalent side, we have 5.82, just simply adding the 0.82 to the 5. And on the milligrams as CaCO3, that'll be 41 plus the 250, so that should be 291. Milligrams per liter as CaCO3. All right, make sense? Good there? All right. Okay, we can double check that we did it right. This is, just the book kind of walking us through it here. Nothing too spectacular, but a little better handwriting here. All right, so next thing I want to kind of deal with, and we've already touched on this with the CO2 natural water system, is carbonate alkalinity versus non-carbonate alkalinity, all of that kind of stuff. So when we talk about carbonate alkalinity, sometimes it's called corrected alkalinity, meaning that the role of any other stuff in the water that's not carbonate has been removed. And so if we're talking about just the role of carbonate, which is the major species typically, if we buffer the water with something, let's say phosphoric acid, you'll see phosphate buffered solutions for biological studies quite frequently. Really anything that has this acid-base chemistry, that we have these equilibrium points, can act as a buffer, and that can effectively be alkalinity. We kind of talked about that last time, right? So some of the protons that we add to the solution are not going straight to a proton that's just hanging out in the water, but rather some of them will be added onto, or if we're going the opposite way, they'll be stripped off of these molecules. So when we add acid or base, at least in some areas where this transition is happening quite a bit, it's not a linear response to how much acid or base that you're adding. So that's kind of a buffering capacity, and in the sense of when we're talking about alkalinity, that's an acid neutralization capacity that the water has because of that chemical. So in the carbonate system, again, that's what we're typically or primarily concerned with. What we can describe is essentially the amount, and here we have moles per liter, the brackets, the amount of species that can accept a proton times the number of protons they can receive, right? So in this case, we have a 1 and a 1 minus, and then we add 2 times the CO3 2 minus, because that one can accept 2 protons. We also have, always going to have the amount of OH minus in the solution. That kind of just refers to where we are on the pH scale, counterbalanced with So subtract the amount of protons we have there. You'll notice this is pretty close to, but not exactly the charge neutrality equation. So this is kind of gets us pretty close to a charge neutrality of just the carbonate species. The corrected aspect would be what's accounting for some other pieces in there. So if we use this corrected version, maybe we are assuming there's no other charged species, then this would be, then we have charge neutrality with just this. Okay, so one thing to consider is we can also write this as the alkalinity in milliequivalents per liter instead of moles per liter. And you'll notice what has happened when we talked about it in moles per liter with the brackets is we had to multiply by 2 for the charge, right? So if we express it in parentheses, where these parentheses are going to be this milliequivalents per liter, that's still essentially a molar unit, but it's a moles of charge, right? So that's incorporated into here, so we can write it the same manner if we really highlight and notice the fact that we are doing it in milliequivalents. Then we can solve our alkalinity problem just by saying, okay, if we put it in milliequivalents, then it's just the sum of each of these. All right, so it's a small distinction, but an important one. All right, so then if we want to consider the non-carbonate alkalinity, really that's just everything else. So if we had the total alkalinity, or I guess you could abbreviate it TALC, so the total will obviously include the carbonate system, but then you might have quite a bunch of other species. I mentioned phosphoric acid. There's some sort of a borate buffer kind of system. Silicon oxides, silica hydroxides can be a part of natural systems. Things like sulfuric acid, so HSO4 minus here. And one thing you'll notice, I don't know if it's quite clear, but we had all these pluses, right? So plus the silica hydroxides, then minus the pH, minus this sulfuric acid, HSO4 minus. We could include, if you're somehow adding H2SO4, it would be minus 2 times H2SO4. The reason they're not including that here is because that's not going to exist as a species in water. It's immediately going to at least dissociate to HSO4 minus. So we're not actually going to include that. This equation is kind of showing us for the species you might find in water. Really, any acids that would have a species at some sort of a pH, so phosphoric acid, all of this. And I think the place that no, okay, so I think they missed something here. This should probably be a 3 right there. I would think this should also be a 3, or they should count that as a 2. So based on the way they're treating this, I think they've got an error. I just copied this from somewhere on the website, some website. So the point is, if we do non-carbonate alkalinity without spending too much time wondering if they're wrong, the non-carbonate would be just simply we get rid of the carbonate terms, and that's everything else, right? That's the point. Okay, and ultimately these systems are governed by charge neutrality. If we're considering what portion of our alkalinity is coming from carbonate versus non-carbonate, at some point, the total alkalinity will be governed by the charge neutrality, but if we're just discounting part of it to understand how much of it maybe we could remove by stripping the system of CO2, that's a different problem, and we might just be looking at it a little bit separately for the moment. Okay, so that brings us to our next set of slides, which is going to be on essentially how do we manage then the alkalinity or softening processes. Okay, so we talked about that. All right, so let's take a moment and make sure we are feeling good about this kind of stuff. So this is example 6.5. We have a sample water at pH 10 with 32 milligrams per liter of carbonate, CO3 minus, and we are tasked to find the alkalinity as CaCO3. So give that a shot for a moment. We're given our equilibrium equations here for CO2 with HCO3 minus and the bicarbonate with carbonate. All right, so I'd like to kind of sketch what should be the process. We've got the book's solutions to follow through here next, but I kind of actually provided these keys here to say, okay, well, what's the CO2 or CO3 2- concentration? What's the equivalent weight for calcium carbonate, so we can make that conversion, and what's the molar concentration of bicarbonate as well. That should give us on the right track if we're trying to find the alkalinity. Remember that the alkalinity is going to be essentially the sum of these acid neutralizing components. We're only given carbonate in this particular system, so we're just going to assume all of the alkalinity is carbonate alkalinity. So we could say, if we solve for the HCO3 minus, it's going to be that plus the amount of CO3 2 minus plus the amount of OH minus, and all that minus the H plus. Now I went ahead and put all these in parentheses. We could also write it like this. Oops. If we're going to solve for the molar equivalence, then we just have to account for the 2 CO3 2 minus that we need. Okay, so either way, starting with these pieces will probably be pretty helpful to get us going with that. Okay, so we know, we should know already the OH minus and the H plus, so we could go ahead and get those out of the way, right? So the H plus should be 10 to the minus 10, because we are at pH 10. We should also be able to find that the OH minus should be 10 to the minus 4. That's coming because we have kind of the inverse. The total of the pH plus the pOH is going to add to 14. That's because our partitioning coefficient for water is 10 to the minus 14. And that Kw we could write as OH times the H plus divided by water, which is 1. That's just from our equilibrium from H2O. Okay, so we should be able to get the pH and the pOH, or get those concentrations from there. Bless you. So then it's really just a matter of solving, okay, well, how much is in HCO3 minus and CO3 2 minus? So we should be able to use our equilibria equations. We'll notice that at pH 10, the concentration of H2CO3 is going to be very small. So we're going to assume it's negligible. So we're just going to, using that, kind of not worry about that whole part of it. Okay, we're just going to simplify, neglect that altogether. We'd have to be have our pH a lot lower for that to become important. Okay, so that means then we can simply use one equation, this K2. We've got it as 4.68 times 10 to the minus 11. And we know, I mean, it's written up there, but this is a way we can get to, all right, how much of our system is in CO3 2 minus versus HCO3 minus. So with that, we can solve for both of them. That'll give us each of those. Earlier, we talked about the equivalent weight for CaCO3. Well, let me just note here, solve for each. Let me elaborate on that for a moment. Given that we assume that H2CO3 is negligible, we can say that our total CO2 carbonate, I guess we'll call it, should be equal to the HCO3 minus plus CO3 2 minus. So this gives us a second equation that we can use to fill in there. Technically, we'd also have the H2CO3, but we're going to assume that's approximately 0. Okay, so this gives us a way to plug in here, or vice versa, rather. It's probably more likely to just plug it in that way. We were given some total amount of carbonate, right? This amount of CO3 2 minus, that's going to be proportioned into each of those, and then we can solve it from there. Now, there's probably two ways to interpret this here, and I guess the total, counting this as a total is probably wrong. So 32 milligrams per liter of CO3 2 minus. That probably means actually that we just simply need to convert from 32 milligrams per liter into moles per liter to find this. So that would come directly there, but that also means that there's some additional amount of HCO3 minus, just the way it's written. So we would solve this guy first, then we don't actually need the total equation since we were given one particular type. So I'm revising a little there, but you can kind of see if that did count as a total, we'd have it one way. So at any rate, let's take a look at what the how the book solves this. The equivalent weight here, this is just going to be 50 milligrams per milli equivalent. We talked about that already, but that would give us then a way to convert into as CO3, right? So the process here makes sense. Okay, sorry if I confused that with using the total. It's good to keep this in mind, but then, you know, as I did, I double checked and probably don't need it because we weren't given this as a total, we were given that as a specific. Okay, so let's make sure we are tracking with the right way to do it, supposedly. So the book here, you know, talks about the equivalent weight of carbonate. We can get that. So of carbonate itself should be 32 milligrams per liter, or excuse me, 30 milligrams per milli equivalent. And then we can convert that 32 milligrams per liter of carbonate by taking that value, the 32 milligrams per liter we were given, divide it by the 30 milligrams per milli equivalent, multiply that by the 50 milligrams per milli equivalent of CaCO3. So that just directly gets us to a value to say CO3 2 minus that we could use in the alkalinity that's already converted to the charge, right? That just gets us there right away. That they find that at 53.3 milligrams per liter as CaCO3. Okay, so then it says the equilibrium is reached very rapidly between CO3 2 minus and bicarbonate, HCO3 minus. So we've talked about that. And so it's saying, you know, it's using this equation that we were talking about. And given that, they then kind of backtrack and say, all right, well, let's take this 32 milligrams per liter, calculate the basically calculating the CO3 2 minus as a moles per liter, and then converting to millimoles so that we can get this answer in millimoles per liter of bicarbonate. So the way I was approaching it was I just went to moles first and figured we'd finish the conversion over to as CaCO3 later. They kind of just jumped straight to the milli equivalents here and then had to deal with it here. Doesn't really matter which way you go, just whatever makes more sense to you. Okay, so then they're converting this to as CaCO3. So we have a portion from the carbonate as CaCO3, that's 53.3 milligrams, and then we have a portion from the bicarbonate, 57 milligrams per liter as CaCO3. And then the only piece left to solve for alkalinity is to get the contribution of OH minus and H plus. Okay, so that's the last piece here they're going to do. They say the pH is 10. So, and we already kind of talked about this, that at, with water, we kind of know, well, first of all, hydrogen, the H plus, it's 1 times 10 to the minus 10 at pH 10. The equivalent weight for hydrogen should be 1 because it's 1 divided by 1, right? So that's pretty simple. The equivalent weight for OH minus should be that, oxygen is 16, hydrogen is 1, so that's 17 total, divided by 1 should be 17. So they're doing hydrogen first, and they get 5 times 10 to the minus 6 milligrams per liter as CaCO3, because we have to multiply by that 50. All that. They continue and get the OH minus the same way. You'll notice I kind of did the mental thing, but the grams per mole of OH minus here. So we're just taking the moles per liter, 1 times 10 to the minus 4th moles per liter of OH minus, times its molecular weight, and then we convert to milli equivalents and multiply that by the 50 milligrams CaCO3 per milli equivalent. So all of that is just kind of that unit conversion stuff we've been talking about. So that gets us 5 milligrams per liter as CaCO3 given that OH minus. All right, so all told, we have the 53 plus the 57 plus the 5, and since our pH is so low, we have such a little amount of H plus, that's minus a very, very tiny fraction here, basically 0 if we're rounding to 1 decimal place. Right, so at the end of the day, our alkalinity here is 115.3 milligrams per liter as CaCO3. All right, see a lot of you nodding. Feel good about that? Any issues? Feel weird? Doing okay? Maybe? Need some? Yeah.
On the balances, why, I just forgot, but why is H plus subtracted?
Yeah, it's a good question. So in our alkalinity term, we're really defining alkalinity as the ability to absorb H plus. And so if we have anything that's adding H plus, we have to subtract it instead. There can be others. It's kind of rare, but if we skip back to when I was talking about, oh, that was the other slides. Let me pull up the other slides for a second. I had this one, I wonder if it'll let me overlay too. There we go. When we were talking about this non-carbonate alkalinity, I mentioned that we had these ones over here, the H plus, but also the acid group here. If we were to use vinegar, that's like, I forgot the exact formula, but it's acetic acid. In the acetic acid form, it should probably be subtracted here as well. So anything that can add a proton to the system instead of taking it away would be subtracted. Those will usually only exist at pretty low pHs, but technically they would be a part of the carbonate, part of the alkalinity system. So we can think of alkalinity again as, it's often referred to as the acid neutralization capacity. You could also notice that if it was meaningful, you could reverse this and have some other term that's like reverse alkalinity, and you could call it the base neutralization capacity. And so you'd be subtracting anything that would be adding an OH minus, that type type of deal. Okay, good question. All right, so what do we do when we want to control, alkalinity is not actually precisely what we want to control, but it relates a lot to the mineral content that we would want to control. And even just talking about CaCO3, you can probably get a good feeling for that. So if we add calcium carbonate, CaCO3, to water, we're getting calcium ions and CO3 2 minus. And calcium carbonate is kind of, it's sort of everywhere. It's very common. And when we consider it in nature, that there will be calcium carbonate minerals all over the place. And so we recognize that there's the carbonate addition, and it would be one thing if we added this where there was protons, right? If we added it in the form of CO3 2 minus, but instead of the calcium, we replace it with 2 protons, that would mean that it's kind of one side's counteracting the other. And if we notice, if we put 2 protons on that, that just becomes carbonic acid, H2CO3, right? So if you stop and think about the fact that we can substitute those protons for a calcium, when we do that, we're adding the mineral, the calcium, and we're adding this acid neutralization capacity. So this carbonate could now accept protons. So having a calcium versus the protons there, it's adding that alkalinity when we do it with the calcium. We can do sodium bicarbonate. That should sound pretty familiar, baking soda, right? So the same type of deal can happen there. In fact, we use that in our cooking. So as we think about all this stuff, we'll recognize that if we're trying to remove calcium and magnesium, we'll notice that the alkalinity is important and similar processes are going to happen. So there are a few ways to soften water, and I hope that we can make some connection here so you can see that role of alkalinity. The major portion, the portion that really has a lot to do with the alkalinity system, is what we would call the lime soda ash process. We're really manipulating alkalinity, the pH, causing things to precipitate, manipulating a lot of the solution chemistry in order to remove minerals. So that's what we're going to focus on. But just as a quick aside, that's not the only way to do it. So we'll say this is our focus next. But first, there is a process we could do called ion exchange. So this would incorporate some kind of a resin material. You might create this sort of like a polymer resin kind of a thing where water could pass over it, maybe absorb some of the water, but it kind of stays intact. So maybe like a bunch of packed beads in a column or something. And this ion exchange resin would be filled with some sort of polymer. Here's an example. And it would have a lot of groups where it has an electrostatic interaction with an ion. So sodium, we'd fill it with sodium, and then it could release that sodium and exchange it for 2 of these sodiums for 1 calcium. So we see in this particular scenario, this segment of the molecule has 4 groups of sodium, and so you could exchange that with 2 calciums. So you could swap it like that, and now you've exchanged the same amount of charge, but if you think back on our ionic strength calculations, ionic strength is defined as 1/2 the sum of each of the charges. In this case, I'll say CA. I'm just going to kind of do, I'll just do it this way. The sum concentration times its charge squared, right? So in this case, we'll pretend there's both sodium and calcium. So if that's our ionic strength equation, even if we have half the calcium, we're multiplying it by 4, right? So we are reducing the ionic strength if we're simply exchanging calcium to sodium. Okay, so we have a system then that can reduce the net charge. That's helpful, but it's also directly removing the minerals that might precipitate or that might cause the hardness issues, right? So the reason we care about hardness is partly the ionic strength effects and that impact that might have on our daily lives, the soap, the whatever, maybe the mineral scaling, right, for industrial applications. So it can have that impact. But the other thing that's pretty neat is you can actually recharge your ionic strength resin if you have a reservoir of a very, very salty environment. So what you'll do is you run it for some time, you exchange everything for calcium and magnesium, you've gotten rid of all your sodium, and then you just have like a reservoir where you put really, really high concentration of sodium, and then the thermodynamics sort of pushes off the calcium because just the total amount of sodium just causes it to be replaced sort of by force. So you flush out the amount of calcium that you got, and then you can actually keep most of that highly salty reservoir. You just put the water back in it, and you just let it sit there. And it can be so rich in sodium that like you can reuse it for a long time. So it's a pretty convenient way to regenerate these ion exchange systems. It's a pretty useful tool. Just wanted to kind of note how that works a bit. I don't think that's quite as used quite as often for like really huge municipal scale systems, but I'm not actually too sure about that. Certainly you can have medium to small scale systems like that. There's probably some large scale ones. But that might not be as cheap as just doing a bit of manipulation with the solution chemistry. So that's what we're going to explore with this lime soda ash process. So we'll get into part of it today. I think we'll finish up next time, but we'll spend the next 5-10 minutes introducing this lime soda ash process. Okay, and I have all these silly diagrams just as the get our minds thinking lime soda and ash, right? But soda ash, that's sodium bicarbonate, is what you could call that. Is that baking soda? I'm like second guessing myself now. Lime would be calcium hydroxide, so CaOH2. One other note here, kind of big picture, the ion exchange can actually do a pretty good job reducing these multivalent cations to a pretty small level. This lime soda ash problem has a bit of an inherent limit. We can only go down to about 40 milligrams per liter as CaCO3. Now that is within our soft water category. So it's actually kind of convenient if we did want not like ultra soft water. We are okay with a little bit of mineral content. That actually, we might as well use that because it's not going to go too far anyway. All right, so when it comes to softening with this lime soda ash process, we essentially have a 5-step plan to make our water soft. That's the deal. Each of these steps is going to accomplish a specific goal, and I'm going to shut that door. since we don't need to be a part of his conversation. Okay. So these 5 steps will take us through kind of a sequence of, well, let's get rid of part of this alkalinity so that when we do change the acid, it's going to have some impact that we wanted it to, or things like that. So the first goal is actually to essentially remove CO2. That's getting rid of a lot of the carbonate alkalinity, right? So to do that, we recognize that dissolved CO2 in some form or another can react with lime, this CaOH2, to yield calcium carbonate. Been talking about that a lot already, right? CaCO3 as a solid. So we can get this in a solid form to precipitate. And what you'll notice is most of what we're doing is trying to remove stuff by precipitating it. So if you think back on like my whole view on, environmental engineering processes, you take stuff out of stuff, you transform it. Here's what we're doing in a lime soda ash softening process is we're causing something to precipitate to remove some aspect. Then we're making some other adjustment. Sometimes we'll have to add more calcium to remove more calcium. It feels a little counterintuitive, and in this case we see that that's exactly what we did, right? We added calcium in the form of lime, and that got rid of a lot of the carbonate that was in the system by precipitating it as calcium carbonate. Okay, so number 2 then is to remove calcium carbonate hardness. And this is going to introduce another concept here. We can define specific categories of hardness. If we're to think about our total hardness, it's going to be, we have calcium and magnesium. Generally, those are the 2 that we care about. So let's pretend for a moment that all we're dealing with is calcium and magnesium. Well, we can categorize it as calcium that will, if given the chance, combine with carbonate. And then maybe we have more calcium than that. And as we'll see, I have a diagram for this. We can sort of categorize it. This is calcium carbonate hardness. If we have a lot of calcium but not so much carbonate, then maybe we say, okay, we have non-carbonate hardness, calcium hardness. We'll see in a minute kind of how that plays out, but we're going to remove some segment at a time based on what can be removed in these processes. So here we would have calcium Ca2+, reacting with our bicarbonate, and again, more lime. So by adding things to the reactant side, by adding in lime to our solution, we can cause these reactions to occur, right? And this is an equilibrium reaction, but we can force it off to the right by adding the lime. So that's going to allow the calcium that's in solution to react with the bicarbonate. So in this case, it's very similar to what was already going on, but we're just spurring this reaction on, adding a little extra lime. Again, we're going to get calcium carbonate as a product. As we form that, we can remove it and take it away from the system, right? So we can precipitate it and remove it, and then now we've had the ability to remove this calcium carbonate, calcium and bicarbonate here, hardness. Basically the calcium that could be removed by reaction with the bicarbonate. Okay, number 3 then is removal of magnesium carbonate hardness. It's very much the same sort of a deal. We have magnesium and we are reacting that with bicarbonate that's in the system. And we're doing so by adding lime to precipitate 2 things. Here we have calcium carbonate again and magnesium hydroxide solid. So we'll be precipitating both of these. And that's, one thing you'll see here is we added 2 calciums and we removed 2 calciums. So we're not really removing more calcium here, but we should be breaking even. but we are removing magnesium, right? And number two, we had calcium in the system and we added the lime. So anytime we see lime here, that means we're adding it, right? So that I should probably make that clear. So the additives would be lime and soda ash. So anytime we see those appear on the left side of the equation, we're adding it, and whatever else on the left side of the equation was already in the water, and that's kind of being removed. All right. So essentially what we're seeing is when we remove the CO2, we're adding calcium and removing calcium. When we're removing the calcium carbonate hardness, we're adding some calcium and removing twice the amount of calcium. So we're getting a net removal of calcium there. For the removal of magnesium carbonate hardness, we're adding calcium to remove magnesium and also get rid of the same amount of calcium that we added. So both are going to happen. Fourth, we're going to remove calcium non-carbonate hardness. And now that we've gotten rid of all this carbonate, different reactions can start occurring. So now that the carbonate's gone, now we're going to add in extra carbonate without adding any calcium to get rid of a bit more calcium. Since we've already took out all the carbonate, now we have to be adding the carbonate, right? And that's where our sodium bicarbonate comes into play, or soda ash. So now we're adding this guy. We're leaving the sodium in there, but we're doing this exchange where 2 sodiums for 1 calcium, we're going to take that trade-off. Okay? So that's going to give us more precipitated calcium carbonate, and then finally we can do the same thing with magnesium. And in this case, we actually have to add in a little bit of calcium since we already took it all out in order to give ourselves the opportunity to precipitate calcium carbonate while also getting the magnesium hydroxide solids to form. Okay, so we actually have to take it all in this sequence because if we've got too much CO2 in the system, it's not really going to work too well. And then we're making use of whatever's left for the calcium and then for the magnesium. And once we've gone past all of the bicarbonate that was in the system that could react and could be used to pull out, to precipitate out as calcium carbonate, then we've gotten rid of all the carbonate hardness, calcium carbonate hardness, magnesium carbonate hardness. Then we go to the non-carbonate hardness. By the way, it's ordered in part in this way where we do calcium first because calcium is has a more favorable reaction to precipitate. It's calcium carbonate that precipitates, not magnesium carbonate, right? That's not the way of it. So when we think about this, it's always calcium first, then magnesium. Okay, if we were to draw this up in a diagram, we could see we have some total hardness across the entire thing here. Some portion of it will be this calcium carbonate hardness, CaCH. So if we remove that portion, what's next is some amount of calcium non-carbonate hardness. So we've removed all of the bicarbonate by here. Then after that, we have magnesium non-carbonate hardness. Now, that's the case where we have carbonate hardness that does not meet all of the calcium. So we see that just all of the calcium here and all the magnesium here. So if we take a look at the bottom section here, if our bicarbonate here was to pass, if this went past this barrier, then we would have no calcium non-carbonate hardness. We would have some magnesium carbonate hardness, and then we'd have magnesium non-carbonate hardness. So depending on the ratio of, of these pieces, that's going to kind of dictate where things end up. So you can kind of think of this graph into two categories. One describing the actual constituents, and then given those, we can identify how much of our hardness can be removed by the different steps that we were just looking at. Okay, so we're going to come back to this. The problems involved really are dealing with understanding kind of how it works, more so than like anything super complicated with different chemical reactions. They'll be important, but it's like, okay, we added this to achieve that. We added that to achieve the other thing, right? So kind of just wanting to give you that picture of it, and we'll resume here next time. All right. Any questions before we go? Okay. So we'll talk more about that, and then probably get into a bit of a disinfection research topic after that.